This is a video that's part of our statistical process control series, and we're going to focus in on control charts today. The learning objectives for this video include comparing control charts to their companion simplified run charts, both time series charts, each a little bit different. We'll also differentiate between control lines and specification lines. We'll introduce the decision tree that's used when we're control charting for different types of data, like whether it's continuous or discrete data, defectives or measurement data, um, a small sample or a large sample. Some of the material I'm pulling up right now on screen comes from the Lean Six Sigma Data Analysis Workbook, and this is a picture of a run chart. We have an earlier video on run charts and how to build and create them. One of the things I love about run charts is a run chart helps us to see central tendency. That's what's drawn in the center line right here. And we get a chance to see the amount of variation based on the wiggle that we see in this line. The concern that we have with run charts is the following. With a run chart, we're never quite sure if these unusually low or high incidents, if they are indication of special cause variation or common cause variation. We really don't know if it's common or special cause. That's the limitation of a run chart. In this next screen, I've got that same run chart, but now I have included customer specification limits in the chart. This is an upper specification limit, and we've got an associated lower specification limit. And we know that spec limits come from our customer needs. We've now identified points of concern, but we still don't know if that's special cause or common cause variation. See, special and common cause variation is determined by the historical data itself. It's identifying based on statistical rules, is this something that is part of the inherent variation built into the process, or is it something that is unique? So if we add spec limits, that doesn't help us. It shows us pain points, but it doesn't help us determine if it truly is common or special cause. In this next screen, though, let me introduce something called a control chart. A control chart is similar to a run chart in the sense that on the x-axis we've got time, on the y-axis we've got output performance. We've got our average or center line, but we've introduced some other statistical phenomena based upon the historical data associated with the process. They're called control limits. Control limits are different than specification limits. Control limits take a look at the natural common cause variation in our system, and then at the plus and minus 3 standard deviation mark, we draw in these control lines. Control limits are based on the inherent variation in the system. They are not based on our customer needs. Control charts also take a look at other statistical phenomena that is unusual in a system. And anytime we've identified something that is outside of the 3 standard deviation control lines, like here, or anytime another statistically unusual phenomena, like 2 out of 3 data points that are beyond 2 standard deviations, or 4 out of 5 that are beyond 1 standard deviation, or sawtoothing, and a variety of other rules. Anytime those statistical rules are broken, we'll call that special cause instances. So the great thing about a control chart that differentiates it from a run chart is it helps you to see what is common, natural, inherent variation, and what is special cause, unique variation that we should swoop down on and make special corrective action to. Again, here is another example of a control chart where within the plus or minus 3 standard deviations, that is normal, allowable, common variation. And it's only these data points that are outside of the 3 standard deviation mark that are special cause. We know that from our empirical rule discussion, this should be only 3 out of 1,000 times. And just to remind you how that relates to normally distributed data and the empirical rule, let's take a look at this next picture. if we were to take each of these data points and jam them up against the y-axis, we'd end up creating that histogram that we studied in earlier videos. And we know plus or minus 1 standard deviation is 68%, plus or minus 2 standard deviations is 95, plus or minus 3 is 99.7%. And so these that are outside, these instances that are outside of 3 standard deviations, they truly are unique from a statistical perspective. They're really just 3 out of 1,000 style occurrences. We're going to call that special cause. The items that are inside those 3 standard deviation marks, we'll call that common cause. One of the most commonly misinterpreted aspects of a control chart is to assume that your control limits are your customer's spec limits, and that's just not the case. Control limits are based on the historical data of the system, sort of the voice of the process. Spec limits are based upon your customer's needs, the voice of the customer. And I've got 4 little thought problems right here for us to work through to help us differentiate between what's a control limit and what's a spec limit. I'm going to zoom in on option A. Okay, so in option A, what I've done is I've drawn a process in a control chart where the control limits have been defined. Those are the ones in blue. And this process I've drawn to be in control right now. But I'd like you to think about where could you draw specification lines so that it is not only in control like it is drawn, but also in spec. I'm going to have you stop the video for a moment, think about that, and then we'll come back. Okay, so we're back now, and I've drawn a process that's in control, and those blue lines are our control lines. And what I want to do now is I'm going to draw in red specification lines where this data is also in spec. So we've got it in control. Let's take a look at where we draw those lines to be in spec. The answer is there's many different places that we could draw these spec lines to show that this is process data that's in control and in spec. I could have spec lines that run like this. All of my data is now in spec, where we've got upper and lower specification limits, and it's also within our control limits. But I could also draw it this way. There's an example where I've got spec limits that are situated so that the process is in control and also in spec. A variety of different locations to draw it both in control and in spec. They don't always have to be right on top of each other. Now let's take a look at option B. So in this example, I've got control limits drawn so that it's in control, where our data is in control, and I'll draw in red spec limits to show that this process is out of spec. I encourage you now to stop the video and think about where you draw the lines to show this being a process that's out of spec but still in control. All right, we're back now, and my guess is that when you were thinking about this, there were many different spots that you could draw the spec lines to show a process that's out of spec, but still in control. So my spec lines will be in red, and if I were drawing spec lines to show this thing to be out of spec, I could do something like this, where upper spec is up here, and lower spec is right here. There's an example where a number of these data points are out of our specification limits. I could also do something like this. I could draw my spec line to look like this. Again, now I've got items that are out of spec both on the high and the low side. I've got a situation though where the inherent variation is manageable. It's part of the inherent process. It's common cause variation, so it's in control, but the process is not meeting the needs of our customer. It's out of spec. Control limits and spec limits are not the same thing. Control limits represent the variation based upon the historical data that has been collected that is tolerable, manageable, part of the process, or common cause, and what data points are falling outside of statistical unusual irregularities that we assign as special cause. Spec limits, on the other hand, are limits that are obtained from interviewing and understanding our customer needs. So to create a control chart, we need to consider the type of data and the size of the data that we're collecting. So we usually run through some sort of a decision tree like this. It might be something you do manually. Most of the stats packages, though, when you highlight the data, it will internally run through a chart like, or run through a tree diagram like this and make the decision for you. But it's nice to know how they're making that decision. The first thing that they do, the first thing that the software does is it takes a look at what type of data. Are we talking about continuous or discrete data? Most of the time, we're taking a look at continuous data, at least in our process improvement coursework. Then we ask the question, how many elements within this continuous measurement data are we grabbing to calculate our output metric? In the catapult case, it was individual shots, so the sample size was 1. If it's a sample size of 1, the name of the chart that we use is sometimes called an IMR chart, or some stats packages will call it an XMR chart. Individual, that's what the I stands for, and MR stands for moving range. So we get a sense of what is the drift and what is the amount of variation in our central tendency, but also what is the amount of variation from shot to shot to shot. Another common type of control chart is something called an X bar R chart. It's where we're grabbing 2 to 5 subgroups as an individual sample and recording its average. So, at the end of an assembly line, you grab 3 golf balls, you measure their diameters, and then you record you record those individual values down and draw out a control chart. We call it an X bar R chart. Again, X bar stands for small sample means. R stands for the range. We'll create charts that show that central tendency and variation as described by range. And then if we've got 10 or more samples that we are collecting, it's often called an X bar S chart, where we no longer calculate variation by simple range calcs. We instead use the standard deviation. So it's called X bar S chart. One of the most popular charts is something called an IMR chart, individual and moving range. And it's actually a pair of control charts where the upper one is a control chart showing the individuals that are being measured. It could be individual shots, individual daily hold times, but the central tendency of the system. And then the bottom control chart is showing the range between each one of the observations that were made. Now, that range is calculated to represent the variation in the system. So central tendency above, variation as measured through range below. For small subgroup samples, that type of chart is something called an X bar R chart. Again, the 2 pairs of charts created, one for the central tendency, the other one represents the variation as described by range. Another type of chart is a U or a C chart, and these are for tracking defectives. Again, look a little bit similar, but because we're counting individual units and we are not measuring the distance from a nominal target, the control lines are going to vary. And so we can see our upper and lower control limits, and it's not a flat line, but it's a line that changes. P and NP charts are not for tracking defects, but instead for tracking defectives. And again, looks just like all of the other control charts. It's for discrete data. And because it's discrete data, we won't have one flat upper and lower control limit. Those values will change. And now what I'd like to do is I'd like to create a control chart using QI macros. It's very easy to do. I'll spend an entire separate video on all of the detailed ways that you can read and analyze a control chart from QI macros from the tool sets inside of QI macros. But let's jump into Excel and see a chart created with QI macros now.